All right, welcome to seminar mathematical physics, and our speaker today is Oleksii Kotov from University of North Carolina, and he's going to tell us about creative manifolds and homogeneity structures.
Thank you. So, if anyone saw my papers on the internet by chance, then here I'm Oleksii. It's the same. It's not like a change. No, it's the same name. Today, I hope it will be at most 1 hour, maybe less. I want to talk about certain things related to creative manifolds and to explain how can we handle more complicated structures by use of vector fields or maybe modular vectors or conventions. Okay, so the simplest part is the following one: is the algebraic part. How well do you see what I mean? Okay, so suppose we have some abelian monoid gamma. Then we can say what is a vector space or module over V graded by gamma. So gamma graded. Module over something. It's the sum. It's a direct sum of elements gamma and gamma capital of E gamma. It means it's a direct sum of some submodules or vector subspaces of homogeneous degree gamma, where gamma is parameterized by gamma capital. And then one can see that this sort of objects, they form a category. So they form a category whose objects are those graded by abelian monoid grade modules or vector space in the simplest case, and morphisms. So their category objects are gamma graded vector spaces or modules, and morphisms are morphisms of the corresponding spaces or modules which preserve the gradient. Which preserve the gradient. Then, so one can see that this is a tensor category. So there's a tensor, well-defined tensor product, where V tensor gamma is the sum, direct sum. So at the degree gamma is the direct sum of all gamma plus gamma 2 equals to gamma V gamma 1 tensor W gamma 2. And then this means that we can talk about associative algebras in this category, so graded associative algebras. Also, sometimes we have a gradient. For instance, if gamma capital is n natural numbers or z or z2, then there is a morphism from z2 which deals with the pairs. So you can talk about gradient or symmetry, because this gradient is close to zero in this category. And then you can also say what is the amount of commutative algebra or supercommutative or gradient commutative algebra. So the gradient gives out the notion of supercommutative gradient algebra. So it works pretty well for finite monoids. There's absolutely no problem. So this is well known it's a basis of the supergeometry when the monoid gamma equals to the 2. Gamma equals to the 2. It corresponds to supergeometry, where we know we can construct everything. But here we have a finite monoid, which I will say that it's the easiest. So this one example. Second, let's take a kind of simple example where n equals to okay, so gamma equals to n. So this is the natural numbers. So let's take polynomials. Okay, let's say Oleksii doesn't matter of some variables x1 and so on xn. And we say that for all these variables, let's call this the first number is equals to 1. And this gives us the natural gradient on the polynomials on the algebra A. So A will be naturally graded. So it's always the sum for t from 0 to infinity, AK, where AK corresponds to the polynomials of the polynomial power equals to K. Well, so then everything is quite easy when we are completely in the algebraic context. So when we have some module or either a vector space like here, when we take an algebra here, we say what is commutative, what is graded, and so on. But what is important here that we always have a direct sum. So what I mean that every polynomial is a direct sum of polynomial homogeneous polynomials of x and dx. Then the problem can start if we try to understand what happens for more general algebras. So this is related to the path to geometry. So let's look again at the example where A equals to C of x1 so on xn. So there's a polynomials of variables x1 and xn. We assume the polynomials has fixed degree 1, but actually they may have different degrees. Then we'll talk about weight polynomials. But let's look at this simple case. There are different ways how to complete this algebra to some other algebra of functions. So one of the ways we can complete this through complex analytic functions. And this completion is given by actually it can be viewed as topological completion given by some echelons. So there all they will be kind of topological completions. This can be completed to smooth functions, complex value functions, or to germs of complex analytic functions. Germs at 0. Or also another my favorite example is form of power series. I didn't call this like this, which is form of power series of n variables. All of them are sort of topological completions. Now the question: what will remain out of the gradient here? Right. So every polynomial is a sum of polynomials of fixed homogeneous degree. But if you look at complex analytical functions, then it's already a convergent series, and it's an infinite sum. If you look at smooth functions, it's even not a series. So it's something. If you look at germs, it's a local series, which in some small neighborhood, sufficient small neighborhood of zero. So the formal power series is a series. Okay, but neither one of them is finite. It's a sum of it's a finite sum of homogeneous polynomials. Now the question: what will remain out of the gradient structure? But we still have some gradient. Right? So let's reformulate the gradient of polynomials using the following vector field. It's called the Euler vector field. Which is the sum of x I d by dx I. Okay, I for 1 to n. So this vector field is well defined. And how to characterize now a P which is the set of F, set of complex polynomials with the degree, which is the same as both in our notations, equals to K. Using this vector field, this is simply the same as polynomials, is A such that epsilon of A equals to K of A. Yeah. Right, so it's easy. Every homogeneous polynomial degree, K is only this and only that, which satisfies this property. Now, you see that this vector field is kind of universal. So we can transform this to all four cases. So it will act on complex analytical functions, smooth functions, germs of complex analytic functions, and formal power series. Let's examine the last case. Actually, they are all kind of, in some sense, they're similar, but not exactly. So this vector field, which is the Euler vector field epsilon, which is the same as the sum for xi dxi for I from 1 to n. It's a vector field, or it's a derivation of A complete, which is the formal power series. Now, you know, the formal power series also contains finite sums, contains polynomials, right? So the polynomials are sitting here inside. And in particular, homogeneous polynomials are also sitting inside formal power series. So how to characterize homogeneous polynomials inside the formal power series? Exactly the same way. So AK can be viewed as those F inside the completed algebra such that epsilon F equals to K of F. So the idea is completely the same. So if you know the formal power series and the Euler derivation, we can immediately restore this algebraic side, right? We know what is homogeneous polynomial. We know that what is every polynomial except that a general function here is not a finite sum; it's an infinite series. So that's the only difference. There's also another theorem which we can check. Actually, it's an easy exercise theorem. If someone will see this in literature, tell me where it's written. I don't know, but it's kind of a simple exercise. So suppose we have an ideal inside A hat, which is stable with respect to the action of this derivation. Then, if and only if, it's always possible to find a finite number of functions fi, which belongs to ai, so they are homogeneous polynomials of certain degrees, such that your I is generated by f1 and so on. I goes from 1 to r, goes from 1 to r. So it means that the algebra of formal power series, everyone knows that polynomials of one variable and thus of any number of variables is an invariant algebra. So every ideal is finitely generated. And also, it is slightly less known, but still known, that formal power series is also an invariant algebra. So every ideal is finitely generated. But what is also nice that those ideals which are preserved by I, they are finitely generated by use of by homogeneous generators. So that it means that they are great Noetherian algebras. So the idea of this proof is very similar to the proof that A hat is Noetherian. So that's not big. So it should go by induction. Okay, so actually this algebra is nice because it's low with only one maximum ideal, the same as well as the algebra of complex analytic functions at zero. But you can see that for smooth and complex analytic functions, you have a similar property. So those functions which are eigenvalues with respect to epsilon will be homogeneous polynomials. So you can still restore this structure inside those using only the Euler vector field, which is acting everywhere. So, and this gives another notion of gradient. There's a generalization to more general monoids, which is so that's some idea. I don't know if I will be able to talk this. I don't want to make it too long. At the very end, there's a generalization of this. It's a more general idea how to do it, and the Euler vector field is suitable for n gradient and z gradient. For other monoids, there's some other idea how to do this, but the idea is kind of similar. So there is an algebra there is some structure. Either it's an action of some vector field, or it's an action of some multiplicative monoid of some group, and then the homogeneous components are precisely the components which are homogeneous with respect to the gradient. But the whole object is not a finite sum. It can be either a limit or it's a smooth limit with respect to some topology and so on. So it means that we have some algebra and we have some structure, which is an Euler vector field or action of monoid or something. And this structure restores completely the gradient algebra underlying this algebra. Now, let me examine another case, which is kind of probably more interesting than n gradient and z gradient. And although any n gradient manifold can be viewed as z gradient, but z gradient is by far more complicated, and it has more features of super gradient rather than n gradient. So let me show you, but I will first I will give you the definition, the local definition of a z graded algebra, how I do it, and then you will see how it can be used in geometry. So what is the z graded geometry using the structure? So suppose we have some ring R, okay, and later it will be some sheaf of rings. But at the moment, suppose it's a ring, so or it's a commutative ring, or it can be actually super commutative, doesn't matter. So today we can all assume that O is not super for simplicity. If there is also some super gradient, then it's additional Z2 gradient, the parity which is compatible with this one. But for simplicity, let us assume that everything is commutative. So we have some commutative algebra. So let's take and assume that we also have some generators x1 and so on. So actually, it's a countable number of them. Generators. And also we assign some weights to them. So I call this boosts, which are some weights which takes values in Z without zero. Right, in the previous case, all the Gauss numbers of all variables and against polynomials, it was only one. But here they can be -1, -2, 700, 4,000, and so on. The only requirement here, which I impose to behave it well, we can define it more generally, but I assume that at each Gauss number, the requirement, so each Gauss number in Z without zero, there exists a finite number of generators. So it's sort of like this. For instance, polynomials of finite number of variables is a good example because there's only weight 1 and there is only n variables at weight 1. So it's nice. Polynomials of infinitely many countable number generators is a bad example. You put to each the Gauss number 1 because it will be infinitely many variables at degree 1. However, if some of them, if they're infinitely many variables, but some of them are degree 1, 2, 3, -1, and so on, and there's only finite each Gauss number, then it's a good example. Okay? So let's consider now A, which is the algebra of polynomials of these variables. And certainly it's a Z-graded commutative algebra. Over R. Okay, so it can be actually a real. It's too much required. But in our case, later you will know. Well, and it's certain degree. So we can always count, since it's a finite number of monomials, for each monomial, we can say what is a beta, right? So this A is the sum of A k to k and z, where AK is the number, so is the set of polynomials, f in R, x1, so on, x, so on, such that the total cost number of this equals to k. And since the weights can be both positive and negative, it means that this is really Z-graded. So it can be something in degree -1, -2, -4, and so on. Also in positive degrees. What is important that what we have in degree 0 is not R. Because for instance, if in general, because for instance, if we have some variable of degree -1, another variable of degree +1, then their product has degree 0. But it's not an element of R. So we put R in degree 0, however, there are more polynomials of the same weight. Okay, then, but this is not the end of the story, because algebraically everything is fine. We can talk about degraded algebras in this context, because it's a finite sum of homogeneous degrees. However, if you want to go to geometry, then normally this algebra is insufficient. We should take either some smooth functions or complex analytical or at least formal. Then the last idea, what I said about the Euler vector field, will work well. And now I want to show some details how it works. So let's construct. Okay, so let's separate. So it's a completely non-canonical procedure what I'm doing now, but later you'll see that what I will get will be canonical. What I will say is the following. So let's decompose the set of variables, x1 and so on, into the subset of variables of positive degree and negative degrees. Okay, so that's all set of variables y1 and so on of positive degrees, and those let's call z1 and so on of negative degrees. So the work of yi is less than 0. Okay, I think I said greater than 0. And the cost of zj is strictly less than 0. Okay, then this algebra can be endowed with a double gradient, right? Because we can count the gradient of with respect to those variables and those variables independently. Okay, so we can now introduce the cost plus and the cost minus. And the cost plus of yi equals to the cost of yi, and the cost minus of yi equals to 0. The cost minus of zj equals to the cost with the minus sign of zj, and the cost plus of zj equals to 0. Okay, so now your algebra will become n cross n. So now A will be n cross n. And your z gradient will be the difference between those two, the plus and the minus. Right? So by construction, you can see. So if you have some polynomial, then you can compute the plus cost number minus cost number, the total cost number, the difference between them, between these two. Okay, so given this auxiliary structure, which is n cross n grade, which if you are working only in Z-grade category, you don't preserve this information. You can somehow exchange the grade. However, in this, until we fix the decomposition of all variables into positive and negative grade, then it's possible. Okay. Now, what we can construct out of this auxiliary n cross n, we can construct two filtrations, and then a combined filtration. So it will be a decreasing filtration. Also, it's called an exalted filtration. So it will start with the whole algebra. So A, let's call this F plus. Let's call this start with A will be the whole F plus, which will contain F1 plus A, which will contain F2 plus A, and so on. And the same for minus. And now I will show what it means. 2A, and so on. And then F plus minus plus minus P of A is the set of polynomials in A. The plus minus first number of each is greater, let's say greater than P. I think greater than. Okay, so it's easy to see that since both the plus and minus gradients are non-negative, how it's written here, they are really an ideals, right? So I mean, each of this is an ideal, because if you multiply a function of positive degree greater or equal to P with any function, the result is a positive degree greater or equal to P, because it's non-negative. And the same for F minus. Okay? Then we can also construct F, the total degree. So let's say F, okay, S of A is the sum of intersections FP plus is FQ minus, where P plus Q is greater than S, or this is the same as functions in A, such that the sum of the ghost plus F plus the ghost minus F is greater or equal to S. Okay, so how it's written here, it seems to have nothing to do with the C gradient, because we introduce some auxiliary gradient, and when we exchange somehow use some change of variables, it's not necessarily true that the new variables, okay, the positive variables will be a combination of positive and negative of negative, if they can be mixed, right? So I mean, this decomposition into the positive weighted, negative weighted, is not an invariant of C gradient, right? It's some auxiliary structure. How these filtrations are constructed also looks like it's artificial, right? It does not depend, it depends. I mean, it looks like it depends on the choice, right? It's not really C gradient, but depends on the choice. But what is remarkable, so it's a very nice trick, that actually those filtrations and the combined filtration, it's characterized only by this structure. And the idea is the following, so you can see, just check, it's again some exercise to see that FP plus is precisely the ideal which is generated by algebras, by homogeneous components of Z degree greater or equal to. So it's kind of final, right? So this is characterized by n cross n gradient. This is characterized only by Z gradient. But what is important that this is an ideal generated by such a subspace. But it's not. I mean, the whole subspace is not an ideal, because if you not take, for instance, homogeneous components of degree P, Z degree P, multiply with some homogeneous component of degree -1, you get P -1. So it's not an ideal. So the trick is that we generate, we take everything generated by those. Then it's automatically an ideal, because if you have some subset and generate the ideal, it will be an ideal, right? So, and what is interesting that this is holding. I mean, the whole filtration, positive filtration, is characterized only by Z gradient, nothing else. And the same happens for minus F minus Q of A is generated by A less or equal to minus Q. So everything which is generated by homogeneous component of Z degree less or equal to minus Q. And then, well, and then we can also construct a combined filtration, right? Because the combined filtration is simply the direct sum for the intersection of FP with F minus Q with P plus Q greater or equal to S. If we can construct this and that, we can construct a combined filtration, of course. Now, so let's see what we can say, for instance, so let's take Fs. What we can say about the quotient of F divided by FSA. So it's an ideal, right? And this is an algebra of polynomials. You can view this ideal in terms of pi gradient. right? Because we can always choose some auxiliary by gradient, although it's not canonical, it exists. Okay, so so this is the set of so the ideal consists of the set of polynomials, the positive and negative degrees, for which is greater equal to s. So how to characterize the quotient? So the quotient is isomorphic to the sum of polynomials a, k. Okay, so this is the sum of polynomials f, for which the ghost number, the ghost plus ghost f plus the ghost minus f is less than s. Right? Okay, and so we have some homogeneous component. We can assume that this has some homogeneous component, right? So because the both plus and minus ghost numbers cannot be computed for an arbitrary f, only for homogeneous components, and then it will be direct sum of them. So if we have this locality property, there is only finite number of variables at each way. What we can say about this quotient? There are only finitely many variables which will satisfy this property, right? Because we have only finitely many at each weight, and we say that the sum of the weights, positive and negative weights, is less than x. So it's only finitely many. So it's isomorphic to R to some finite power. Okay, and this actually will be very nice in the geometrical construction. Okay, so now what we can do is that, like we constructed the completion of polynomials to form power series, we can complete the same here, right? We can construct the completed algebra. A, which is the direct, so it's the inverse, sorry, it's inverse limit of A divided by Fs A. For S. Sorry, do I need to explain what is the inverse limit and the inverse system, or everyone knows that? Everyone knows. Okay. So if not, then I can do this in a few minutes. Otherwise, we'll do this. Okay, we have indeterminate quotients, right? For each S, there is a quotient. And if some S is greater than the previous one, there is a quotient by quotient, right? So for instance, there is a quotient map from A divided by F1 to A divided by F2, because F2 is greater than F1. So it means that there are projections. If you call this quotient AS, for instance, then there is a projection from AS to AS plus 1. Yes, and then it will be compatible. If it compose two projections, we projections like this, right? We make a triangle. And then it's possible to define the projective limit. And in the case of formal power series, this will be the algebra of polynomials, and this will be all polynomials of power greater or equal to s. And the projective limit will be decided from power series. But here it's somewhat more complicated. It's weighted polynomials. Okay, so and the filtration also is more complicated, right? So it's constructed. So what we construct will be an algebra. It will be a commutative algebra. It will be commutative R algebra. How can we restore? Well, when we do this, we immediately forget about n cross n gradient. Now it's not needed, right? Because this filtration is constructed out of Z, right? Constructed in some such simple way out of Z gradient. The quotient is constructed from this data, and the algebra will be, I wanted to say graded, but now it's a question graded in which sense, right? Because each element now will be not a finite sum, it will be an infinite sum, it will be form of power series or weighted form of power series. Okay, so the question, how can we restore the previous information? How can we see that everything is coming from some weighted polynomials? Just exactly the same way. So we construct the derivation, which is the sum of cost xi times xi dxi for I belongs to some set of indices, possibly infinite. And this will be a vector field or derivation, so it will be derivation of a cap. And then we can see that homogeneous polynomials of some homogeneous way will be precisely the corresponding eigenvalues here. So nothing else. So all the information which we had before is here. So the algebra of polynomials is sitting inside. The algebra of homogeneous also is sitting inside. So no, I'm very sorry. So it's not completely true what I'm saying. So no, it's not true. The algebra of polynomials now is not sitting inside, but we can still talk about homogeneous components. And what is sitting inside? So there are homogeneous components here. So we can say what is A hat K. So this is the set of F which belongs to A hat such that epsilon F equals to KF. So homogeneous polynomials are examples, but not only. So these are some form of power series in general of some homogeneous degree. Then there are two ways. So normally people do? They take the direct sum of different A hat K and then say that this is an algebra of polynomials. But what is so the algebra of the graded algebra? Because then it's really graded. But what is bad? Then I will show it just in a minute. That in the geometrical context they will not give a nice sheet. However, if you look at the whole algebra with the Euler vector field, where the homogeneous components are defined as eigen subspaces, then it will be a sheet. So, and the next, so I think I have some time. So the next part will be about geometry, which is behind it. So I want to show how can we construct Z-graded manifolds. That's what we call with my collaborator, Vladimir Salnikov, semi-formal, just some terminology which emphasizes that there will be functions which are formal with respect to some parameters, some variables, and smooth with respect to other, smooth or analytical with respect to others. So and let's see what happens in geometry. And this is how to construct. This is how to construct a Z-graded manifold. So now it's geometry. So those who work in mathematical physics, you know that, for instance, in mathematical physics or in PDD, there is a procedure called homological perturbation. And in the homological perturbation, you take formal power series with respect to Gauss number. It means that for practical purposes, so we need to have formal power series. And this is how the algebra goes to geometry. So suppose we have M, so it's a smooth manifold, or it can be convex analytical, but let me work in the simplest possible case, it's a smooth manifold. Assume that we have a cover, open covering, UI, such that the open alpha, such that the union of alpha is equal to M, it's a good covering. So then let's fix an open set, which possibly one of those. So there are by R, as R we take the sheaf of smooth functions over U. So now assume that we have variables like before, some number of countable number of variables, and for each of them we have a Gauss number which is belongs to C without zero. Then we can construct the algebra, which is the A hat, which is the inverse limit of R x1 and so on, divided by the filtration which we introduced before. And this is R A. Then, what do we get out of it? So as we have seen before, when we take the quotient by fs, the quotient is isomorphic to R to some kind of power, right? So if R is a sheaf, then the quotient will be automatically a sheaf, right? Because it's just the sum of R is a sheaf. For instance, it's the sheaf of smooth functions or the complex analytical functions or something. Then it will be the direct sum of finite number of sheaves. It will be a sheaf. And then the projective limit of sheaves, it's always a sheaf. Okay, so what we'll get will be a sheaf. It will be a sheaf over U. And then what is the Z-graded manifold in this? Well, what else we can say about this sheaf? So this sheaf will be endowed with the Euler vector field, which was constructed as before. And we can say that, so it's a sheaf of algebras, and we say that morphism of these break morphisms of the sheaf of algebras are those morphisms which are commuted with the Euler vector field. Right? Then, how to construct a Z-graded manifold? So we have a union of open covers that over each open cover we can construct such a sheaf, and then we require so for each open U alpha we construct such a Z-graded sheaf in this sense. And over double overlaps, we have some Bloom condition. So it means that over double overlaps, there is some isomorphism of sheaf which respect the gradient in this sense. So we can use the Euler vector. Then the structure which we'll construct will be what is called a locally ringed space. And in addition to this locally ringed space, this will be an Euler vector field which will keep all the information about the gradient. So we'll say that Z-graded manifold is a locally ringed sheaf modeled by the sheaves of this form. So it's a sheaf, it's such a formal competition together with an Euler vector field. And morphisms are those morphisms of locally ringed sheaves which is coming with the Euler vector. Why we cannot take the direct sum of homogeneous components why it's bad in the sheaf theoretical language? So in fact, many theorems can be proved by use of homogeneous components. For the homogeneous components, we take here homogeneous functions, homogeneous polynomials of degree k. Here the intersection of the side view with homogeneous polynomials of degree k, and then take the formal completion, I mean, degree-wise. And we'll get AK hat. And then the naive approach is that we take the direct sum of this AK. And in many cases, in many proofs, it's sufficient to have AK for different k. However, the direct sum, so what I want to say, so the direct sum of A hat K is not a sheaf. And this was actually, there are examples, this is even true, not necessarily for Z-graded, it's also true for N-graded. And this, in particular, it was explained by Jan and Rudolf in their papers. So the idea that, in general, the direct limit of sheaf is not, as a sheaf is not a sheaf. Right? If you take the direct sum of homogeneous components, it will be not a sheaf. And the idea how to see that it's not a sheaf is quite easy. So suppose we have some infinite Booth power. So with Ui, where I belongs to n. So let's take choose some sections as I, which is a section of this algebra AI, for instance, degree of course number of Si equals to I. Okay, so now let's choose functions Fi with support inside Ui, and we also choose such that the support of phi I and phi j is empty if I is not j. It's always possible to do this. Then let's take okay, let's multiply phi I with Si and call this sigma I. These are well-defined sections. They are compatible, so they are compatible over double overlaps. So for the sheaf, it's always possible to construct a section such that the restriction gives phi I as I on each I. But then if you take the sum of them, you'll see that the degree will be not bounded because we have homogeneous components of each degree. So it means that if you take the naive direct sum of homogeneous components, you will not achieve. However, if you proceed like this, if you take such a portion, then the projected limit, then the Euler vector field, then all homogeneous components will be sitting inside as eigenvalues, eigensubspace with respect to Euler vector field. And what you'll get will be really a sheet. Okay, and now maybe just a bit more about smooth Z-graded manifolds. As I said, many things can be proved using only homogeneous components. But however, this keeps me somehow nice because it's general. We get a local ring space type for free. And now a little bit more about the smooth case. As I said, Z-graded manifolds, they behave like rather like Z2 than N grade. And I will show you the difference. And then one more theorem about the bachelor theorem and the relation between another category of smooth Z-graded manifolds, and then we are done. So now we are talking about smooth Z-graded manifolds. So what kind of structures are here are canonical? So we have these completed algebra functions, which is filtered. So this is the same as F0 of A hat. So the filtration will be now on the whole structure sheaf or the whole linear space. This will be F1 sitting inside this one, F2 sitting inside that, and so on. Now, and this everything living over the base M. What kind of structure do we have now? Do we have a projection to M or invariant of M inside this space? So just your guess. So if there is an invariant of M inside this equated space, it means that there should be a projection of the algebra functions on this equated space, which is a cap of algebra functions on it. If there is a projection, that other way around, the algebra functions here can be embedded into the algebra functions. In your opinion, what exists?
The spaces themselves can be Z-graded manifolds over itself.
Yes, of course, yes. But I mean, we construct the Z-graded manifold as before. So we have some open covering of M over each set. We take polynomials of some number of graded variables, we take the completion, and over double laps, we have the change of coordinates. There is canonical filtration. As I said, it depends only on Z-graded. So there's an algebra function here, and there is this algebra of formal power series. So in which direction do we have an embedding for projection? Now you can switch your knowledge of supermanifold. So suppose a supermanifold, we have a supermanifold. What do we have canonically? Is there is canonical projection onto the base or embedding onto the base?
There's a canonical
Geometry.
projection onto functions on the base. So there's a canonical map from the base into the supermanifold.
There is canonical map from the base to the supermanifold, precise. And the same we have, right? If you call this, so M and the functions of M is this A hat, then there is canonical embedding of M inside M curve. And this is given by the following projection. So we have A hat, and if you take the portion by F1 of A hat, we are paying precise the functions on F. So it's easy because here we take the portion that's F1 is generated by all functions of neither positive nor negative degrees, and the portion is precisely there. Do we have a projection? So if there is a projection from n to M, then it should be the embedding of functions here into functions here. So the naive way is to look at functions of degree 0, of a hat of degree 0. But it's not good, because if you have negative and positive degraded functions, then for them you have degrees, may have degree 0, but they're not coming from the base. Okay, so it means the projection M to M calibrated does not exist in general category, because it's not canonical. However, in the smooth case, like for smooth supermanifolds, there is a Bayes-Shor theorem. And the Bayes-Shor theorem says that there is a Z-graded vector bundle over M, such that your M is isomorphic to the total space of this Z-graded bundle. And this is precisely the same what happens in the super case with the Bayes-Shor theorem for smooth supermanifolds. So it means that for smooth supermanifolds, every smooth supermanifold is diffeomorphic to phi, what is called parity shift of fibers for some vector bundle. But in the complex analytical case, it's no more true. There's the whole industry around this split or non-split manifold. There was in the paper Witten about that, right? We don't again Witten about that, so it means it should be counted of high quality. Well, it's well known that in the complex analytical case, the Bayes-Shor theorem does not work. But in the smooth case, it works, and the same happens for Z-graded manifold. So, and then what happens in the Z-graded, smooth Z-graded case? So we always have some V. So it's a vector bundle, Z-graded vector bundle over M with an Euler vector field. Which now can be counted as smooth vector field on a smooth manifold. I assume that it's finite dimensional. If it's infinite dimensional, it's somewhat more complicated. But assume that it's finite dimensional. Then what happens? So there are smooth manifolds with the Euler vector field. So it's some special vector field. There are zero locus of which is the base, and around zero locus it has some integer eigenvalues. So actually, it's I don't have time to explain. It's a little bit complicated to characterize this Euler vector field intrinsically. It's more related to the action of S1 rather than usual vector fields. But I would like to skip it now for now. And then, given such a structure, we can construct a Z-graded manifold in our sense, in the sense of locally ringed space. In the sense of locally ringed space. The Bayes-Shor theorem says that this map is subjective. So it means that every Z-graded manifold can be obtained like this. So in this fourth category, the Bayes-Shor theorem says that this map is subjective. Well, it was our long, like years ago, theorem with Vladimir Sanik. Actually, the proof is very similar to the one for supermanifolds. We use so what is important that we use this filtration, this kind of filtration, so then at each level we prove that show that some sheets are solved. So it's, if you look at the any proof, textbook proof of Pescher's theorem for supermanifolds, this is quite simple. What is important that we have formal power series, of course. Otherwise, if it's a finite sum, it will not work like this. Okay, so but now here, since there's smooth manifolds together with Euler vector fields, we can define another category whose objects are those smooth manifolds with Euler vector fields, and morphisms are smooth maps combined with Euler vector fields. It's obvious that it will be a morphism from this category to that, because if we have here a morphism which commutes with the Euler vector field, here we have the great morphism, and as I said, there are those morphisms which are commute with Euler vector field. So there is a funder in this direction, but what we proved recently in our theorem with Valentina is that it's also subjective. I mean, whenever we have some morphism of this, as we say, semi-formal manifolds, so degraded manifolds by use of formal local gradient spaces, then we can always switch it to some smooth map here. So it's somewhat more complicated. The theory which here we use the degraded version of the Barrel theorem, and also geodesics maps of some complete metrics. So, but it's very technical. So the most important part is the gradient Barrel theorem, which I don't have time to talk about. Okay, so that's all. Thank you.
What are the theorem for smooth finite value?
No, it's okay. It's the following one. So there is a Barrel theorem which says the following. So suppose we have a point and some formal power series at this point. Then in general it corresponds to Euler to the Taylor coefficient of some smooth function. If it's convergent, it will be analytical. If not,
This is what I thought.
yeah, exactly. But what happens in the graded case, what I said, it's more complicated. So suppose we have weighted polynomials, so all variables, they're also weighted. They have some integrals. And suppose we take a formal power series, which has some pure weight k. Then it's always possible to construct a smooth function, which has eigenvalue k with respect to this Euler vector field, for which is the Taylor expansion. So it's somewhat more complicated. If we just do this naively using the Barrel to proof of the Barrel theorem, you immediately lose the gradient. So this is some sort of here you use some sort of theorem about monoids, but solving certain type of defines and equations. There's some trick about that. So what is good about that? So whenever again it can be generalized. So instead of Taylor series at one point, we can use a Taylor series in the transversal direction for some submanifolds. Because it will work perfectly well. So if we have Taylor expansion with respect to transversal variables, it's always possible to find a smooth function with this transversal Taylor expansion. And the same works in the graded case. So it means that every function here, which is the formal polynomial, formal power series of fixed degree k can be written as smooth function here of degree k with respect to the Euler vector field. And what we prove is the following one, where we have some homogeneous map here, which in some sense can be viewed as at least locally as some number of functions of different homogeneous formal power series of different degrees, but it's locally. Globally, it's more complicated. Then it's always possible to find a diffeomorphism here, which is homogeneous with respect to Euler vector. So then it's somewhat more complicated. So that's about the Barrel. So that's what I call the graded Barrel. Means we can always control the degree, not only the weight, not only lift it somehow, but preserve the weight.
There are also some recent attempts in precise geometric quantization. But also in this direction, we use Borel theorem, this version, but the pointwise. I cannot provide the name now, sorry. The precise version. It's another, in a different, from different perspective.
As I said, so that what is kind of, except for this theory about category, which is quite recent news from this year. So the rest, okay, so about this filtration, that's what also understand recently. If you will, I wrote, I mean, there's something picture I wrote about this. We are writing our paper with Vishnikova about graded manifolds. We will cite some explanation what this graded means. Otherwise, the Barrett's theorem existed before, so before some years ago. What is kind of new is that at each level, Z graded is not just the direct sum of graded components. Then you lose a lot of information. We cannot work here. We don't know what is Z graded smooth manifold, Z graded complex analytical manifold. But whenever we talk about graded by some either Euler vector field, or one can say that can be some torus action or monoid action, depends on what kind of monoid is taken. Then you don't need using any more polynomials. So then it can be any function algebra like smooth and complex analytical, formal, and so on. So there's everything kind of unified.
But these gradings also for the infinite ring case, for the rings with infinite coordinates.
This algebra is
Textbook, very nice.
this algebra is infinite. So
of gradings of
yeah, we don't require this finite dimensional. Okay, sorry. This theory, well, let me say. So the Barrett theorem was proved by use of locality. So only there's finite number of variables at each degree. So the Barrett theorem will hold for such a setting. So then this theorem that every morphism here can be lead to a smooth morphism was proven only in finite dimensional case. I didn't know, and then also the Barrett theorem was proven in the finite dimensional case. I still don't know how to do this for infinite dimensional, but the benchmark holds for by use of the locality. And the whole construction of Z-graded manifolds perfectly works if the number of variables is infinite, but there is only finite each degree, so it doesn't matter. So we immediately obtain a shape.
in Python Manifolds, that can be in Python Manifolds. The answer thing that can be this monarch version.
To be honest, so well, we used it's funny, but we used in our paper with Sweating cycle, we used only F minus. So we did some kind of small. So every proof was correct, but there was some small. We mislead this that it's always possible to use F minus and take the completion degree wise. However, if you look at the direct sum, it's not a sheaf, and then it's not clear what is the sheaf containing everything. But if you use the combination of positive and negative filtration, then degree-wise it will produce the same, but then you'll have the sheaf which contains everything. So the Euler vector field, which distinguish inside them the graded components. So then it becomes much easier. So we do have some locally ringed space inside which there are homogeneous components.
Is there a version of Z-graded
I'm not sure I understand.
And you're playing, so you could have Z-graded manifolds. My question is, so maybe the story for spending times and
Yeah, probably there can be many versions. So I'm not sure I have one in mind. So there can be very naive one, like if we play some scheme and try to construct this over a scheme, but maybe it can be something better.
for Taylor series, you need the smoothness.
Yeah, but it can be somehow auxiliary. So if our default is a quotient by some finite group, this finite group can act kind of upsphere that one can construct avoid everything. So this is probably related to manifolds graded by finite groups, but I try to say more.
stacks.
So the right stacks, right? We can have everything. So we can have group weights, So it depends on what can be used as a stack,
No,
right? So
in this
well,
you know,
in this,
it
yes.
wouldn't satisfy
I,
the cycle.
in my opinion, the easiest version of a stack, if you don't want to go outside the smooth category, the easiest version of stack is this pink shoe backhand theorem, theorem about that stack is the proposed modularity equivalence. Of course, it works perfectly here. But about some other stacks, I am not a big expert in this in stacks in the high generation. But in this smooth category, of course, it's.
But then what would be, what would replace the vector fund?
What is the replacement of
Well,
vector
but
fund?
it would be some kind of vector.
Yeah,
Theorem with something from the vector side.
yeah, we can play the same here, right? Try to do local and then do it.
Yeah.
Yeah. Because I absolutely I don't have time to talk about this because then of course there is more time than 1 hour. But actually, what we are writing now with Vishnikova, it's kind of this works in other categories, not only with smooth. Like as I said, by construction of this nice filtration, I put some auxiliaries into n cross n gradient, which is compatible with Z. Then I construct this filtration that's shown the filtration does not depend on n cross n, so it depends on Z. It's a very nice property of Z gradient. However, the question whether we can construct n cross n gradient compatible with Z or not. In the smooth category, apparently yes, because the base row will be n cross n gradient. It's just a vector bundle. In the complex analytical, the answer is no. In this, because if you have n% rate, we automatically have the projection into the base, which does not exist in the complex analytical category. So the answer is no. However, it's always possible to cover the graded manifolds by n cross n. And this can be also each truncation level. So if you quotient A had by Fk, it can be counted as Z-graded truncated manifold, and then each of them can be covered by finite n cross n. And somehow this will capture information about characteristic classes in the complex analytical case. But again, it's still not written yet, so that's why I'm not talking about details.